So you must remember that in our last class on stellar structure we derived this relationship. You see, this kappa LR divided by 4 pi square AC R to the power 4 and TR cube, right? So this was basically the radiative transport equation. Fine. So you see, in this class I am going to talk about this very particular term, and this you must remember we called as opacity coefficient kappa, also as a function of R. Now as you can see, this opacity basically determines the flux that can be transported by radiation for a certain temperature gradient or more to the point. How large the temperature gradient must be. Let me again say this. So basically what this term determines is the flux that can be transported by radiation for a certain temperature gradient or more, and that also to the point how large the temperature gradient must be in order to carry a given luminosity, this L, by radiation. Okay. Therefore, you see, this opacity kappa is a very important quantity that has very large effect on the structure of the star. Now what we are going to talk about today is basically the various physical processes which will contribute to opacity. So today we will talk about the various sources of opacity. Okay, now you see, the very first important source is electron scattering. Okay, now when an electromagnetic wave that passes an electron, what does it do? Basically, it will cause the electron to oscillate and radiate in other directions, like a classical dipole. Now, this scattering of the incoming wave is equivalent to the effect of absorption and can be described by the Thomson cross section. No, this P will not be there, just M. Thomson cross section of electron, and let me write it down. This cross section is basically 8 pi by 3 E square by me c square whole square, and this has a value of 6.65 into 10 to the power minus 25 centimeters square. Okay, now the associated opacity coefficient because of this is due to the combined cross section of all the electrons in a unit mass of gas, and this is obtained by dividing this Thomson cross section by sigma by Ne or mu E mu, and so we have, you see, divided by mu E mu, and this is equal to 0.2 into 1 plus x. This will be plus x centimeter square per gram. Now you see, since the electron scattering opacity here, this one, is there any dependence on frequency? No. There is no dependence. Since this is independent of frequency, this expression also gives the Roseland mean. And you see, in this last equality, we have assumed that the gas is completely ionized. And in that case, if you will remember our old lecture, in the case of a completely ionized gas, we can write mu E as 2 by 1 plus x. And this we have used over here. Okay. Now, electron scattering is an important opacity source in an ionized gas that is not too dense. When the degree of ionization drops, okay, this is important, you must remember. Then what happens? So, you see, when the degree of ionization drops, and that happens for less than 10,000 Kelvin in a hydrogen-rich gas, then the electron density becomes so small that the electron scattering opacity is strongly reduced below this value over here. Okay. Okay, so basically what we learned is this particular expression. This is important. So, and also we observe that there is no frequency dependence over here, right? Now, so this was the first important contribution to opacity electron scattering. Now let me talk about the second source, which is bound absorption. Okay, so bound absorption. You see, this process, what happens here, basically this process involves the absorption of a photon, causing the transition of a bound electron to a higher bound energy level in an atom. Now clearly the strength of this absorption is highly wavelength dependent or frequency dependent, but it also depends on the ionization and excitation states of the atoms in the gas. Now, as we have seen previously when we were discussing the Saha equation, the ionization and excitation levels are temperature dependent, and deep in the interior of stars the gas is completely ionized, and so the bound scattering is only important in atmospheres. Now the reverse process is when the electron drops to the lower level, low energy level, and emits a photon. Now this is included in the emission coefficient. Now the third is bound free absorption. Now what happens in this case? Well, this process occurs if a photon has sufficient energy to completely strip an electron from the atom and ionize it. Now in this case, the absorption will have an upper bound to the wavelength based on the minimum energy needed to ionize the atom. But all shorter wavelengths are allowed, as the extra energy can be distributed as kinetic energy of the newly freed electron. Now, as in the case of the bound absorption, the strength and wavelength dependence of this absorption vary according to the ionization and excitation levels of atoms in the gas. Consequently, the opacity due to this process is temperature dependent and is also important in atmospheres. Okay, now recombination is also possible, and it is basically an emission process. Okay, now let me talk about the third part, Here we have free, no, not third, so basically fourth source. So, and this one is free absorption. Now we know that, right? A free electron cannot absorb a photon and simultaneously conserve energy and momentum. But it is possible for a free electron to absorb a photon if it is in an unbound interaction with a nearby atom that can accept the excess energy and momentum. So what will happen? What will happen is that in this case the electron is free before and after the absorption, and so the opacity is non-zero across all wavelengths. Now the opposite of this effect is Bremsstrahlung. That is when a decelerating electron emits a photon. Okay. Now you see, so we have talked about roughly the four basic sources to opacity. Now you see there is an important term called Kramer's opacity. So what happens is that when averaged over all wavelength, the mean opacity due to both bound free absorption and free absorption. So bound free and free absorption behaves, their opacity behaves like this, you see. Rho to the power, rho divided by T to the power 3.5. This is a dependence, and this is known as Kramer's opacity law. This is a very important concept. You must remember this. Now, this behavior, you see, holds only over limited ranges in temperature and density. For example, free absorption actually increases with temperature at low temperature and density with the increase in free electron density. Similarly, bound free opacity cuts off at high temperatures at which the atoms are what? Fully ionized. Okay. Now, there are also additional sources of opacity which are significant, especially in low mass stars. Right? And what are they? They are basically molecules and H minus ions. Hydrogen. Okay. So we have talked about the four sources of opacity. So they were 1, 2, 3 and 4. Electron scattering, then bound absorption, bound free absorption, and then free. Right. So we considered these cases. Now I would like to talk about another important concept which we have already discussed previously in quite detail. So we have talked about gas pressure, remember, and we have also talked about radiation pressure. Now I would like to talk about what happens when we compare these two. Let's discuss, spend some time over it. So as we have previously discussed, in the interior of stars, basically star, and here we not only have ions but also electrons and photons. Okay, fine. Now for most stars, with the exception of being very low mass ones and stellar remnants, the ions and electrons can be treated as an ideal gas and quantum effects can be neglected. And in this case we have, you see, Pi plus Pe plus P due to radiation, and we can write it as P gas plus P due to radiation. Right. Okay. Now this pressure, gas pressure, is basically given by NKBT. This we have also discussed previously, whereas we have also even written it in a different form using the mean molecular weight, and so we also wrote this in this form. Okay, now we have also talked about this concept. Fine, where this mu depends on the composition of the gas and also the state of ionization. Well, mu being given by this relation. Where this is the concentration of hydrogen, then this is the concentration for helium, and this belongs, this Z is 1 belongs to the heavier elements. So we have discussed this. We have also discussed this relation, and regarding radiation pressure, we already know that it is given by this expression. Fine. Okay, now so the next question is this one, is that is, in which stars are gas and radiation pressure important? So to do that, so basically I am talking about comparison. So we know that P gas is equal to R by mu rho T, and P radiation is equal to 1 by 3 A T to the power 4. Now let us equate them, and upon equating them you will see that this becomes equal when T to the power cube is equal to 3R by A mu rho. Now let me show this result, and so basically what we observed is T cube is equal to AR by 3R by A mu into rho. Now let us do a plot, and upon doing this, you see, if we do this basic rough plot, then what we have here is the slope of 1/3, and on this part is gas dominated, gas pressure dominates, whereas this part is radiation pressure dominates. Right. So what we observe, you see, is that the gas pressure is most important in low stars. Low mass stars, whereas radiation pressure is important in high mass stars. And so how can we say that? Well, you see log T. So here on this part is gas dominated, gas pressure dominance, and this happens for low values of temperature. And where is that possible? This is possible for low mass stars, right? Whereas in high mass stars, the temperature is very high in the central part, and this causes the fusion, the advanced stages of fusion, right? Whereas in low mass stars, we have hydrogen or helium fusion only. There, the central core temperature is not very high to sustain advanced fusions. Fine. Now, let's see what happens in the case of our sun. So, for the sun, let us ask this same question: gas versus radiation. Which one is dominating? So, now to do that, we have to write down first what are the various conditions for the sun, the core of the sun. Well, I am giving you the data. So you see the central core temperature is of the order of 1.6 into 10 to the power 7 Kelvin. Well, the density is 150 gram per centimeter cube, and Also, let's talk about composition. Composition is here. You see, y is equal to 0.64 and z is equal to 0.02. Now notice this thing, it is just 0.34. What does this mean? Well, this means that hydrogen is almost half gone compared to the initial or surface composition, where the surface value is around x is equal to 0.7, right? Surface values. Okay, now if we use these values and then we calculate the mu, then you will see this yourself, that value of mu comes around 0.83. Okay, so now let us do this ratio, radiation versus gas, and this is just 1 by 3 A4 divided by R by mu rho into T, and this is mu A by 3R into T cube by rho. And if you calculate this, then you will see that using these values and also the gas pressure constant, okay, value of R, then you will see that this comes around 7 into 10 to the power minus 4. And so what does this mean? This means that in the sun, radiation pressure is much less than the gas pressure. Okay, so radiation pressure is not at all important in the center of the sun under these conditions. Okay, good.